In order to do all the fun stuff in the lab, there's some basic lab calculations that you're going to need to do. Thankfully, things aren't so bad. With just some fundamental calculations, things like C1V1 equals C2V2, things like making solutions from solids, making solutions from liquids, getting comfortable with the idea of sorts of master mixes and serial dilutions, all of these things can really take you a long way in the lab and let you focus on doing all that fun wet work stuff. So today I just want to take you through this guide that is free to download. Basically, it just gives you kind of a cheat sheet of some of the key conversions, some of the key with examples and graphics, as well as links to posts, videos, playlists, all these various things with more information and figures you can look to for reference. So let's just go through these things one by one, just to take a quick look through some examples and some of the basics. And then know that it just basically takes practice, lots and lots of practice. Things get a lot easier over time. But these are the sort of key things to focus on. And once you can nail these, you can really go really, really far in the lab and focus on all that fun stuff. So let's get the not so fun stuff out of the way. The most important thing that you could do is to get comfortable with metric conversions. Often when we're talking about biochemistry, molecular biology, these sorts of things, we're dealing with really small units. We're dealing on the scales of milli, micro, nano, sometimes even pico. Basically, there's 1,000 micro in a milli and 1,000 milli in a base. There's also 1,000 nano in a micro. So all of these different things, all you have to do is move your decimal places, your decimal point 3 places, and you should get to the point where you can easily do this in your head, kind of like second nature. So when you go and you weigh out 0.010 grams on your scale, you can just simply think, oh, yeah, that's 10 mgs, because if I move the decimal place 3 points, I get to 10 mgs. So just kind of get to the point where this is second nature, and you don't even have to think about it. This is really common, especially when you're dealing between microliters and milliliters, between milliliters and liters, between milligrams and grams. Those are some of the most common ones that you're going to be doing in the lab, so try to get to the point where you can do them automatically. Don't worry if it takes you some time, and know that no matter what sort of conversion, you can always sort of work your way to it through dimensional analysis. With dimensional analysis, all you have to do is line things up, line all these conversion factors up in a way that makes the units cancel out, leaving you with what you want. So when in doubt, try out dimensional analysis, and it will typically take you where you need to go. Speaking of knowing where you need to go, well, now you need to be able to convert between things like the molecular weight and molarity and weight volume and all of these different forms, these ways in which we talk about concentration and how we can calculate how to get the concentration that we want. There are different ways that we can talk about concentration, and one of the most common ways that you'll see in the lab is molarity, which is mole of solute per liter of solution. And the same metric units apply, so a micromolar is going to be 1 part solute per 1 million liters. And so these are just things that you're going to have to get used to, but molarity is one of these key ways that we talk about the concentration. So how do you get to molarity? Well, if molarity is moles per liter, well, we need some way to get between that and some sort of weight. So like we need some measure of grams per mole. Thankfully, we can get that from the molecular weight or the formula weight. Molecular weight, or often abbreviated MW, or formula weight, often abbreviated FW, these terms are typically used interchangeably, although technically they're different. Molecular weight refers specifically to a covalent compound, whereas a formula weight can correspond to like an ionic compound, a complex, maybe a hydrate, sort of like the thing that you buy it in. So I like to think about like a bar of Rolos. The formula weight would be for the whole pack of Rolos, whereas the molecular weight would be kind of for an individual Rolo, assuming that when you put the Rolos in solution, they kind of like open up, the package opens up. And so much more on that in other posts. But in practical purposes, molecular weight and formula weight are often used, the terms are used interchangeably, and you often see molecular weight written even when something is a formula weight technically. No matter which of these you have, molecular weight or formula weight, you can convert it to molarity. If you know the concentration in grams per liter, molarity is that concentration in grams per liter divided by that molecular weight or formula weight, and that'll give you the molarity that you want. If you have the molarity that you want and you want grams per liter, well, now you just have to multiply that molarity by the molecular weight, and that'll give you grams per liter. Especially for you protein biochemists out there, you might be dealing with the molecular weight in terms of Daltons or kilodaltons. Often we're talking in terms of kilodaltons. A kilodalton is 1,000 Daltons. What's a Dalton? A Dalton is just a grams per mole. So if we have a molecular weight in kilodaltons and we have molarity, and we want to figure out mgs per mole, we just take that molecular weight in kilodaltons, we multiply it by the molarity times 1,000 because we're dealing with kilodaltons. If you were just dealing with Daltons, you wouldn't need to multiply it by 1,000, and that'll give you your mgs per mole. Thinking back to our idea about kind of metric conversions, mgs per mole, well, that's the same as a grams per liter. The mgs just cancel, the milli just cancel out, you get grams per liter. It's also the same as micrograms per microliter. So again, these are some of the conversions you just want to kind of get used to doing in your head. If you have the molecular weight in kilodaltons and you have the mgs per mil and you want to get to molarity, well, now you just do mgs per milliliter, or remember that's the same as grams per liter, divided by the molecular weight in kilodaltons times 1,000. And again, if you didn't have a kilodaltons, you were in Daltons, you wouldn't need that times 1,000 parts. And so with any of these, it might seem like, how do you remember all these? Well, you don't really have to remember all these, just remember the key kind of what the molecular weight means, what molarity means, and then just dimensional analysis your way to the answer by putting things together, lining things up in a way that is going to make the units cancel out to leave you with those units that you want. There's also some other sorts of forms of concentration that you might see used. One of these is going to be this one that I hate, but it's percent weight volume. A 1% weight volume is 1 gram per 100 mils. So basically percent weight volume is grams per liter times 100%. It's often used for dilute aqueous solutions, especially in medicine. The reason why is it comes from the fact that water has a density of 1 gram per mil at room temperature. And if you add a little bit of solute, that's not really going to change that. So if you say that there's 1 gram of something else in there in your 1 grams per mil solution, that's basically saying you don't have any water. It's all 100% of it is going to be your thing. And so if you have like 100th of that, well, that would be 1%. In order for this to really be true, the thing you're adding has to have a similar density to water, and there's just a really, really, really tiny amount of it compared to the water, so that it's not taking up so you don't have to worry about the sorts of density really changing when you add the thing. And therefore 1% is going to equal 1 gram per 100 milliliters. This one is one of them that kind of like I always have to double think about, but you might see it used occasionally for various things. You might also see things like percent volume, which would be your volume of your solute versus your volume of solution times 100%. For all of these, you want to know that basically you're dealing with the final volumes. And so you want to do your combinations in a partial volume and then adjust to the final volume that you want. Much more on this in other posts, but basically remember that whether it's a solid you're adding or a liquid you're adding, those are going to take up space. And it's that total volume that you want. So sometimes what can happen is the solid takes up space, the solutions, the liquids can actually kind of interact like ethanol and water and change the volume. And so you want to make sure that when you're making a solution, you're measuring to get the final volume when you're actually doing the measurements, like physically in the lab. So you can calculate how much liquid you should theoretically need, but it might be a little more or a little less, depending on how much space the solute is taking up. Much more on this in other posts, but this kind of brings us into the idea of making solutions. There are 2 sorts of basic scenarios to find yourself in when making solutions. One is that you're making solutions from solids, in which case you're going to have to take into account molarity as well as grams per liter, mgs per mil, whatever you want to do it in, but some sort of weight volume percentage and the desired volume. And you'll calculate things that way. The other situation is that you're doing dilution calculations to make solutions from liquids. In these cases, here my favorite formula ever, C1V1 equals C2V2, initial concentration times initial volume equals final concentration times final volume. Let's go into a little more detail about each of these situations. Starting with making a solution from a solid. Remember that molarity is moles per liter, molecular weight is grams per mole. So if you take your molarity, multiply it by the molecular weight, you're going to get your grams per liter, so your weight volume. Remember that grams per liter is the same as mgs per mil. Now, so if you want to get the needed mass for making a solution with a particular molarity and a particular volume, we know the desired volume times the needed mass, which things will cancel out to give you the desired concentration. Therefore, the needed mass is equal to the desired concentration divided by your desired volume. Sometimes it's really impractical to weigh out exactly that needed mass that you calculate that you'll need. In these situations, it's often easiest to weigh out a mass that's similar to what you want, at least what you need, and then to adjust the volume accordingly. Much more on this in a recent post and video, but this is really common if you're dealing with measuring out small amounts. If you don't weigh exactly what you were planning to, well, now all you have to do is figure out how much of the solvent you need in order to still get that final concentration that you want. So if you have, what you can do is take your measured mass divided by your needed volume equals desired concentration. So your needed volume is your measured mass divided by your desired concentration. Here's an example for making a 5 mg per ml solution of BSA. If you only need 100 microliters, which is 0.1 mils, remember 1, 2, 3 points moved to the decimal place will give you your 0.1 mils. 5 mgs per mil times 0.1 mils equals 0.5 mgs. So a really tiny amount. So if you weigh out about 5 mgs, say you actually weighed out 9 mgs, 9 divided by x mil equals 5 divided by 1. You get x equals 9 over 5 equals 1.8 milliliters. And so this is just an example, and there will be lots and lots of examples that you'll encounter over the years. One of the things that you might encounter over the years too is making mistakes. It's really common if you accidentally miscalculate, maybe you have a little too much mass, maybe you overshoot and you have a little too much volume. There are typically ways in which you could salvage the solution. If you weigh out too much, you need to calculate to adjust the volume to match. The measured mass is divided by the total volume needed is going to be your desired concentration. So the total volume needed is going to equal to the measured mass divided by the desired concentration. The needed additional volume is going to be the total volume minus the current volume. But remember that you should really be doing things in sort of like a graduated cylinder or something, so that you're making sure that it's the final volume you're getting to, not just adding additional volume. What if you have too much volume? Now you just calculate the mass. Total mass needed divided by current volume equals desired concentration. So the total mass needed is equals to the desired concentration times the current volume. And the extra mass needed is equal to the total mass needed minus the current mass. So here are just a couple of examples to help you kind of contextualize things. Another way to do this is to calculate the mass you need to add directly rather than first finding the total and subtracting. So to do that, take the extra value, figure out the extra volume equals the current volume minus the intended volume. If you're trying to get to 100 mils and you have 110 mils, that would be 110 minus 100 is 10 mils extra. So you would then figure out the extra mass that's needed for that. Extra volume times desired concentration will give you the extra mass needed. If adding that amount will not appreciably change this final volume, just add it. If it would change it, then calculate the mass for an even higher volume with enough wiggle room so that you can basically add the mass and add more liquid and get have room for both, getting to that final concentration that you want. Because at the end of the day, it's that final concentration that's what you care about. So maybe you end up making 125 mils instead of 100 mils, but you still have that concentration that you desired. Speaking of desired concentration, sometimes the way you're going to get to your desired concentration is starting from liquids. Stock solutions are really common. They're basically higher concentrations of things, of components that we want to use so we can dilute to get to our working concentration, the concentration we're actually using things at. By having solutions at these higher concentrations, we don't have to keep making those solutions over and over and over again. We're able to store them with less risk of kind of things growing. Various benefits of stock solution, which I go over in other posts. Sometimes, so here is just basically an example. When you're dealing with these dilutions, you're going to be dealing with C1V1 equals C2V2. So here, if you had stock concentrations of your buffer tris pH 8, 1 molar, NaCl 5 molar, you can then calculate how to mix these together to get to the to a solution that has 10 millimolar tris pH 8, 100 millimolar NaCl, and 250 mils. All you have to do is C1V1 equals C2V2 for each of the individual components, and then bring the volume up to where you want. Notice that here I was able to combine two different stock solutions in order to get one solution. And I would have been able to mix these same stock solutions in different proportions, and even with different other stock solutions, in order to get a variety of different solutions from those same stock solutions. So yes, stock solutions are super duper important. You're going to be able to add some of it to all sorts of different solutions and still have plenty of room to add whatever else you want to add. In this case, the stock solutions were given in terms of their actual molarity, but sometimes you'll be dealing with stock solutions that are given in terms of relative concentrations. You're going to see things like the X factor. So basically, you might see something that's labeled 10x or 50x or 1000x. The number before the X is telling you kind of how concentrated it is in relation to the working concentration, so how concentrated you want to use it at. So a 10x means it's 10 times more concentrated than you want. 50x would be 50 times more concentrated than you want, and 1000x would be 1000 times more concentrated than you want. So if you want to figure out the needed volume of the stock solution, well, you want to take your desired total volume divided by the X factor, and that will give you the needed volume. If you have 10x, for example, and you had 10 mils, 10 mils divided by 10x, basically what you're going to get is that you're going to need 1 mil of your stock solution per that 10 mils. If you were 50 mils, when you had 50x, it would be 1 mil per 50x. If it was the 10x, you would have 5 mils per 50x. And similarly, if you had 1000x, that would be like 1 mil per 1000 mils. And if you had the 10x, and you had 1000 mils, that would be 1000 divided by 10 is 100 mils. So again, these are just things that you're going to have to get used to. But the relative concentrations is something that you're going to need to know. You might also need to go the other direction. So if you know the volume of the stock solution you want to use, then multiply it by the X factor to find the total volume to dilute to. So if you have 10 mils of a 10x solution, 10 mils times 10 is going to be 100 mils. So you take that 10x solution, 10 mils of that 10x solution, you would need to dilute it to 100 mils in order to get a working concentration of 1x. So again, more posts on all these things to help you figure things out. One other thing that kind of just comes with practice is serial dilutions. These are a series of stepwise dilutions in which you're diluting a thing by the same factor each time. This factor we call the dilution factor. If you're doing, say, halving the solution, the concentration each time, your dilution factor would be 2. So each time you're changing the concentration by 1/2. And you can figure, basically you'll put the liquid into one tube and then use that tube to dilute the next tube, use that mixture to dilute the next tube, up, down, up, down, up, down, into the next, up, down, up, down, up, down, into the next, up, down, up, down, up, down, into the next, across. And this lets you cover a wide range of concentrations. You can actually calculate the concentration just by knowing the dilution, like which dilution number it is, as well as the initial concentration. So multiply that initial concentration divided by 1 over the dilution factor. So if you were halving things, it would be 1/2, and then raise the number of dilutions to get the concentration of that dilution. One last really, really crucial thing is to kind of get used to making master mixes. Determine which reagents, which chemicals are the same in each reaction mixture, and then mix those things together, making enough for all reactions and a little extra to account for volume loss and transfers, and then add that to the parts that are different. The easiest way to do this is by actually making like little tables. So use some sort of spreadsheet software or something. Make a table that says how much you need per reaction, and then how many reactions you want to make worth, and then it'll tell you how much of those you need of each. Remember that your master mix should only contain the ingredients that are shared and not the ingredients that are different. You're going to add the master mix to the ingredients that are different in order to get the final volume, the final concentration of everything that you want. So make sure to leave room for those unique parts. And so you can see that in this example, you have these different reagents that are going to be added to the RNA. That's going to be different per each sample. You want the 50 microliters of total sample. The RNA is not in there, so you're going to have 48 microliters of your master mix per reaction. Note that here, even though I only was doing 8 reactions, I was preparing as if I had 8.5, so that I had extra volume in case to account for things like volume loss during transfer. In this case, I was trying to save reagents. I was trying to save chemicals. You can see hot ATP. So basically, I was using radioactive ATP, and I didn't want to have a lot of extra waste. But if you can, if it's not something hazardous and it's something cheap, always try to prepare even more than that, extra. What I really like to do, if I'm able to, is to make 2 times the amount I want and a little extra so that I can redo things if I need to. But you should always have enough that you can at least reasonably account for the volume that you're going to lose during the transfers. Things that are stuck in the side of the tube, et cetera, et cetera. So hope this helps. I know that it's a lot to kind of take in, but over time it gets a lot easier. And hopefully this will help you kind of know what sorts of things to focus on and how to really prepare if you're going to go work in a lab, and some sort of just a quick reference guide for when if you get lost.